everyone. Thank you very much for coming to my presentation. The topic that I will present is about the use of artificial intelligence for the modeling of surface water resources with special focus on stream flow and water quality. So, first of all, I will tell you that what changes that I have made with respect to the comments of the committee members during the pre-defense. So, one of the major comments by all the committee members was that I should make a better story, one story, and focus on one problem. So I reformulated my research problem, slightly modified the title as well to focus on two of the surface water quality problems, and also rearrange the studies. And the second comment was about that I should add more discussions. And then the third comment was by Professor in that the model agnostic post-processing techniques, the SHAP or other techniques that I use should not be confused with the causality models or causality. So I applied a causality model on my data and compared that result with the model agnostic post-processing results, model agnostic interpretation results. And then another comment was by Professor Lee that the LSTM model that I was using had used very little amount of historical data. On the other hand, the catchment usually depends on the catchment's outflow. They use a very large, they depend on very large amount historical data, for example, 1 month or more than 1 month. So I compared the performance of LSTM using different amounts of historical data. So I will present 4 studies starting from introduction and ending with the conclusion and my future plans. So first of all, I will tell you that why I chose modeling. So the reason is to choose modeling for surface water resources is that whenever we try to solve a problem related to environmental or surface water resources, it starts with observation of the data or data gathering, and then we do some modeling, and this helps in understanding the processes, and then in turn finally we convert our understanding or knowledge into products and services. So in this whole process, the modeling actually plays a very significant role. So therefore, I chose modeling in my research. So two problems that I focused in my research are related to the surface water quality problems. One is about microbial water pollution, and the second one is about the harmful algal blooms. For microbial water pollution, I chose pathogenic bacteria as a target, specifically fecal indicator bacteria. And the sources of fecal indicator bacteria in surface water are numerous, starting from animal manure and human feces and septic tanks, etc. On the other hand, for harmful algal blooms, I chose the chlorophyll A as the proxy of the harmful algal blooms. And this is a serious problem in Korean surface waters in Korea. For example, here we see the harmful algal bloom at Hamon-Weir in the Nakdong River. So when it comes to modeling, there are two major paradigms. One is process-driven modeling, and the second one is data-driven modeling. And the process-driven modeling is in process-driven modeling we write the equations to describe the processes that govern those to describe the processes. And the limitation of process-driven modeling is that they are we make simplifications about the processes because they cannot handle more complicated more complexities. Yes.
Sorry to interrupt.
Yes.
I can't really see the slide moving.
Okay. You are on the first slide.
Yes. You're still on the first slide.
Okay, let me share it again.
Can you go into the presentation mode?
So
I'm supposed to see the slide moving, right?
So can you see this? No.
No, it's not really good.
You have first in the slide mode, and then you have to share the screen. Start share first.
So all people are supposed to see the screen shared through Zoom, right?
Yes, yes, yes.
Okay, okay.
Okay, so I was talking about the two major paradigms there in the modeling. One is process-driven and the data-driven modeling. In the process-driven, I mentioned that they cannot handle the complexities, or it is difficult to handle the complexities, and because we make simplifications. And the second problem is about the computation time. They require a lot of computation time. On the other hand, the data-driven modeling can handle complex situations more relatively easily. For example, land use change, and they also have the advantage that they are computationally fast, especially the inference time is very fast once we have trained the model. So the process-driven model that I used in my studies is the HSPF model, which stands for Hydrological Simulation Program Fortran. This model divides the study area into small HRUs, which are the hydrological response units, and the HRUs are formed by the combination of land use and the subbasins. And then the processes are each process is modeled in an HRU, and then there are processes which are then there are processes which are modeled within reach, and reach is actually a segment of the stream within a subbasin. And in the HRU, it simulates soil water, groundwater, and subsurface flow and sediment transport. So when it comes to HRU formulation, the HRUs are formed by the combination of land use and subbasin. So if we take this subbasin, so there are 4 kinds of land uses in this catchment. So if we are to make HRUs within this subbasin, so we will get such 4 HRUs for this particular subbasin. So similarly, we will get the HRUs for the other subbasins as well. And finally, the processes are modeled within these HRUs. On the other hand, for data-driven modeling, there are 2 common algorithms. One is the decision tree-based algorithms, which are based on simple rules. For example, here a simple decision tree is trained to predict the equalize using the climate and hydrological data. It is trained on just 3 samples. That's why the tree is very simple. On the other hand, another data-driven modeling approach is based on the neural networks, and the neural networks have the advantage that they can, especially in this case, I'm talking about the recurrent neural networks because we want to simulate the time series data. So these recurrent neural networks have the advantage that they can they take the input at particular times at previous time steps, and they can extract the temporal features from the sequential data. And the way they are trained is that they predict the output, and we compare it with the true outputs, and then we calculate the loss. And this loss information is actually used to calibrate the values of the weights or the parameters of the neural networks. Within a cell here, these are the equations which are calculated for each cell, and in the cell there are 3 inputs and 3 outputs. And the cell state, output, and hidden state, these are the outputs from the cell, and the input xt and the hidden state at the previous step, and as cell state at the previous step, they are used. These 3 are the inputs for the cell. So in this, using the cell state and the hidden state, these recurrent neural networks have the ability to capture the temporal patterns. Then for the harmful algal blooms, we know that the chlorophyll A or the harmful algal blooms in surface water, they are dependent upon they have very dynamic relationship with the amount of outflow to be released from the reservoir. And in this case, if we want to improve the water quality, we have to find out what is the amount of outflow that we want to allow out from the reservoir. So in this case, the problem is that we don't have the true labels. We cannot train it using the previous machine learning algorithm which I showed. So that's why I choose the reinforcement learning for this. And in this case, the target of the reinforcement learning algorithm is to find a policy or to learn a policy so that which reduces the chlorophyll A concentration or which improves the water quality. So in the last study, I focused on this problem using. So overall, based on these problems, my research objective was to use the artificial intelligence-based techniques to develop water models related to surface water quality, with special focus on E. coli and harmful algal blooms. And I also wanted to compare the data-driven models with the process-driven model to find out that where the process-driven model is better than the data-driven model and vice versa. So in the first study, I developed a framework which can allow us to improve to make the data-driven models for hydrological data. And then I showed its applications. And the first application is to simulate the surface and subsurface flow. And the second study is using that flow information to simulate the E. coli. And in the third study for the harmful algal blooms, I used the reinforcement learning for the weir operation control. So in the first study, the target was to develop a tool which can improve the rate and quality of data-driven modeling for the hydrological time series data. The problem is that there are several machine learning libraries, but they all focus on one specific task, for example, hyperparameter optimization or model building or data pre-processing like this. But there is no library which combines all of these into one, which combines all of them. So the purpose of this, so what I chose was to combine these already existing libraries and make a uniform interface to perform all the different tasks. So in this, I show the previous studies, libraries which are especially targeting the environmental data scientists and the first one is the neurohydrology, which is for the building deep learning model in PyTorch, but it does not support any other library like other libraries other than PyTorch. The PASTA's library is for the analysis of groundwater time series, but it doesn't support the model building. The ML-Air library supports the model building and post-processing of the results using TensorFlow. However, it does not support other libraries, other machine learning libraries like scikit-learn or PyTorch. And flow forecast is only for the PyTorch and only for the model building and training. It doesn't support the hyperparameter optimization or model comparison. So we see that all of these libraries, they have their specific tasks, but they also have their limitations. So I built a framework. I built a framework which combine all of these tasks and like one framework for uniform interface to do all of these tasks. So here, this framework consists of several submodules, and each submodule performs one specific task. For example, the pre-processing submodule performs the data transformation or imputation of the missing data or HLU discretization. Then this is the datasets submodule which fetches the open source hydrological datasets into the Python. And the models, hyperop and experiments submodules are for the building models, hyperparameter optimization, and model comparison. And then there is post-processing module, submodule for the post-processing of the results or explanation of the model using the model agnostic methods such as shape, line, permutation importance, or partial dependence plots. And also this also helps in visualizing the neural networks. One specific feature of this framework that I wanted to focus is the declarative model definition. In this definition, we define the model using a human readable JSON file, and no matter what our model is, whether it's like in this case it's LSTM, in this case it is temporal Fourier transformer, and in this case it is a regression decision tree. So no matter what our model is, the method to define the model is same. So this helps us. This is more simple as compared to writing the code in Python. Another advantage is that all the hyperparameters of the model are stored in this config file, and in this way it helps us to regenerate the results or reproduce the results. And we know that reproducibility is one of the major challenges in machine learning based modeling. So this kind of declarative model definition and storing all the hyperparameters and the state of the model in the config file helps us to reproduce our results. So overall, the summary from the conclusion of this study was that we developed a framework which I think can improve the rate and quality of the hydrological based data-driven models. And the novelty was that it is an open source and it is written in Python. In the second study, the objective was to build the objective was to simulate surface and subsurface flow and compare the performance of machine learning and process-driven models. I chose HSPF as process-driven model and LSTM as a representative of the deep learning model. And this study was carried out in Laos, which is located in the south of China, and it is the study area is located along the Mekong River. And this is the catchment. So here we have the observation point, and the reason the simulation time step in this case was 6 minutes, and the reason we chose 6 minutes specifically was because we had the meteorological data available at 6-minute time step. However, we wanted to simulate at the main objective was to simulate at sub-hourly time step, and the reason for to simulate sub-hourly time step is that this is small catchment, and this is a small catchment. So in this case, the processes are like the flow or the E. coli, they vary significantly within hours. So if we have time step greater than hour or greater than hour, we will miss certain peaks. So in this study, I developed three models. The first model was the process-driven model, and the two models were LSTM-based models. For process-driven model, I used HSPF, and first I performed sensitivity analysis to find out the most sensitive parameters. Then I performed the calculation, and then this calibrated model was used for prediction. For LSTM, there were two kinds of LSTM-based models: the simple LSTM-based model and the HRU LSTM-based model. I performed the hyperparameter optimization, and then the optimized hyperparameters were used to train the model again, and then I performed the prediction. This is the architecture of the HRU-based LSTM that I used, and the reason for this architecture is that I have mentioned previously that HSPF has HRUs, and it simulates the processes within an HRU. And I wanted to make a one-to-one comparison between LSTM and HSPF. In this case, I assigned one LSTM for each HRU. So the data for one HRU is given to one layer here, this parallel layer, and it produces a surface and subsurface flow for each HRU, and finally we add them together to produce the total surface and subsurface flow. So here is the output from the HSPF for surface and subsurface flow. We see that the HSPF overestimates the surface runoff and underestimates the subsurface flow. Another interesting point here is that the subsurface flow during first 2 years is low as compared to the subsurface flow during the last year, and this can be attributed to the change in the land use in this study area. We see that there is an increase in the teak plantation in this study area, which is a potential cause for the increase in the subsurface flow during the third year. And this is a result from the simple LSTM, and this shows that the simple LSTM model captures it captures the peaks. However, most of the times the peaks are underestimated. And here I show the lag time of the three models compared to the observed data. What I found is that the HSPF model reacts very quickly to the precipitation. So whenever there is precipitation, in this case the two precipitation events, so HSPF reacts very quickly and very it reacts to the precipitation more sensitive to the precipitation. On the other hand, the HRU-based LSTM and the other simple LSTM, although they have in terms of prediction performance, their performance was high, but they were not as sensitive to the rainfall events as compared to the process-driven HSPF model. So here I show the results of the HRU-based LSTM model, because we know that HRU-based LSTM model can predict the flows within an HRU. So my target, I show that for each HRU surface and subsurface flow. What is here interesting is that most of the HRUs, they don't react, they don't show any output. The surface and subsurface flow is 0 for most of the HRUs. Although the performance is high, that means that the overall cumulative sum of these flows, surface and subsurface flows, matches closely to the observed surface and subsurface flow. However, the flows within an HRU, they are not, like most of the time they are zero. And the reason I think is that the model architecture that I used does not account for the interaction between the HIUs. Although in reality we know that there is interaction between the HIUs, water can see from one HIU to the other. So I think that if we use one such neural network architectures which account for the interaction, for example the graph neural networks, which have the inherent ability to to connect nodes. So I think we can improve, make progress on this problem. So overall summary of this study was that we were able to simulate surface and subsurface flow at sub-hourly time step, and we compared the HIU-based model with the LSTM model, process-driven model, and we found that the LSTM model performs better than HSPF, and simple LSTM is better for the surface runoff, and the HIU-based LSTM is better for the subsurface flow. The next study is to simulate the E. coli, and it uses the flow information from the previous study, and I use the 6-minute time step in this case, and the reason for using the 6-minute time step is that the E. coli dynamics in this catchment they changes within 1 hour. I used LSTM as a as a representative of the machine learning model, and the HSPF as representative of the process-driven model. Another objective of this study was to is to show the impact of pre-processing and post-processing techniques on the results of machine learning models. And I used the SHAP and SHAP as a post-processing technique and data transformation as a pre-processing technique, and showed their results. So the reason this plot shows that why I chose the sub-hourly time step. So in this case, this peak, for example, this peak is it finishes within an hour. It takes about 30 minutes for this complete peak. So if our time step is more than hour, it means that hour or more than hour, it means we will miss this peak. So the objective, that's why I chose sub-hourly time step for these studies. So the overall workflow for this study was similar, was to use the flow information which was simulated in the previous study, and then use the bacteria source information in the form of like how much manure was applied to the field, and then the land use change information into an LSTM model to predict the E. coli. Here is the result from the HSPF and LSTM model for simulation of E. coli. What we see here is that very large number of peaks from the HSPF model. And in the previous study, we saw that the HSPF model predicts very large number of surface runoff. Like the surface runoff peaks from the HSPF were very large. So I think that the peaks here from the HSPF are because of the overestimation of the surface runoff from HSPF. On the other hand, the LSTM does not have this behavior of predicting a very large number of peaks. When it comes to comparing the individual peaks or storm events, here we see that the E. coli from HSPF is more responsive to surface flow. On the other hand, the E. coli in LSTM model is more responsive to the subsurface flow. And this is because if this is the E. coli simulated, right? Here is the simulated E. coli from LSTM, and here is the subsurface flow. And we see that the E. coli is more closely follows the subsurface flow in LSTM. On the other hand, in HSPF, it follows more closely the surface runoff. Another important point here is that we see in LSTM we see a falling link here, like in the E. coli prediction. On the other hand, the HSPF doesn't have this behavior. It suddenly drops to the E. coli prediction, suddenly drops to base value. So next, I wanted to show the impact of data transformation on model performance. So here is the distribution of my original data, the E. coli data, and these are the distributions. I applied several transformations, and these are the resulting distributions. We see that some of the transformations only change the scale and do not change the distribution. On the other hand, some transformations change both the scale as well as the distribution. So I compared, I applied each transformation on the model, on machine learning model, and trained the model, and then observed several performance matrices. So in this case, one lesson from this is I drew is that different distributions, different transformations behave differently with respect to different performance performance metrics. For example, robust transformation performs best for the R square, but when it comes to RMSE, we see that only centering performs better. And although RMSE and R square, these are the performance metrics which are more sensitive to the outliers, but still the behavior of the transformation for these two performance metrics is different. Another observation that I made in this from these plots is that that making the data distribution Gaussian-like, more Gaussian-like, does not necessarily help in improving the model performance. For example, here we see that these like log transformation and these two are the power transformation and quantile normal transformation. They all convert our original data into more Gaussian-like, but however, the best performance is not obtained using these transformations. So the next, I wanted to apply the model agnostic interpretation technique to explain the behavior of the machine learning model, and I use Shapley for this. And Shapley is based on Shapley values, and the purpose of the Shapley values is to calculate the reduction in the model performance as a result if we remove one feature. And Shapley is actually an estimation of the Shapley values because when the number of features increase more than 3 or 4, Shapley values cannot be calculated. So I formulated the problem in such a way that this is the test data, and in this case we see that there is a peak here for sample number 42. So I wanted to find out that how does the Shapley explains this peak event. So here is the Shapley explanation for the sample number 41, which is just before the peak. In this case, it shows that the solar radiation plays the most important role in deciding the model prediction. On the other hand, for sample number 42, which is the peak event, it says that the suspended particulate matter and water level they are far more significant as compared to solar radiation. So this conforms with our background knowledge that when there is a peak in the E. coli, it must correspond with a high level of precipitation, which in turn causes the suspended particulate matter or the high water level. The reason water precipitation is low here can be postulated that this was a 6-minute time step data. So like at that particular time step, maybe the precipitation is low, but it was high in the previous time step, which is represented by here like large contribution of the water level and suspended particulate matter. So Professor Im mentioned that I should not, there is a difference between interpreting the model agnostic results in terms of causality. So the machine learning models, at their best, they only capture the patterns in the training data. However, they cannot capture the causal relationship between input and output. So I applied this algorithm, PCMCI algorithm, which is an algorithm to find out the causal relationships between the features in the time series data. So these algorithms, I would like to focus on this plot here. This shows that what is the causal dependency of the E. coli at previous to the other input features at previous time step. So it shows that the E. coli data has more dependency for the water level and precipitation and suspended particulate matter. On the other hand, when we see the Shapley values for the model, it says that the solar radiation was more important for the prediction as compared to precipitation. And this may sound a little bit counterintuitive that precipitation should play more important role as compared to solar radiation for E. coli simulation. And here we find out that the causal model, when applied to our data, shows a better cause-effect relationship. So the summary of this study was that we can use LSTM for modeling E. coli at high temporal resolutions, and it performs better for when we build the machine learning models, it is better to monitor more than one performance metrics because they behave differently. Then in the fourth study, which is focused on improving the surface water quality in the Nakam River, and my objective was to reduce the chlorophyll A concentration, and the chlorophyll A concentration in the surface water is dependent on it has a very dynamic relationship with the amount of outflow from the reservoir. And I chose reinforcement learning combined with the SWOT model for this weir operation control. And by weir operation, I mean that the amount of outflow from the reservoir. So this is the setup of my study. this study was carried out in the Nakung River and at Haman River, and here we have an agent. The job of the agent is to predict the actions in the form of amount of outflow from the weir. So agent tells that how much water to be given out, and then this amount of then we use the SWAP model to simulate the relationship between this water and the water quality in this reservoir as well as the new water level. So SWAP tells us that what will be the new water level and what will be the new water quality. So this water quality is used to calculate the reward, and the new water level is given as input to the agent. So actually agent takes the input, the water level as in the reservoir as an input, and the reward is used to train the agent. The job of the agent is to increase the reward, and the reward here in this case is like how much deterioration or improvement is in the water quality. So I trained this agent for in this case 250 episodes. One episode consists of training the agent for 1 year. So in this case I trained the agent for 1 year 250 times, and it shows that like when with the training there is an improvement in the reward, there is an increase in reward, and corresponding there is a decrease in the chlorophyll concentration. And what next I wanted to find out is that this is the best state of the agent. This agent is at this stage the agent was performing the best in for these episodes, and at this point the agent was worst because it was just the starting point. So I wanted to compare that if I use this agent and this agent, how much the water quality in this reservoir changes. So in this plot I show that this is the first episode and this is the best episode. So I show that the overall reduction in chlorophyll is uniform, and due to which we see these smaller peaks are vanished. And then I also wanted to investigate the impact of different reward formulations. So the purpose of reward formulation is to get the chlorophyll concentration and tell the agent whether it is good or bad. In these two formulations, the reward formulation is relatively simple. We just tell -1 or +1, like bad or good, based on the chlorophyll concentration is above a certain value or not. However, in this case, in the first and here, the reward formulation I would say is more aggressive. That we want to decrease the chlorophyll concentration until it is greater than 1. So we see here that in these two cases the convergence is more, the improvement is more visible in this case as compared to in simpler reward formulations. So this shows that if we have better reward formulation, we can get better results from the reinforcement learning in this case. So overall summary of this study was that we showed that we can train an agent which can learn how much outflow is to be how much outflow should be given out from a reservoir to improve the water quality. And the novelty of this study is that we showed the successful coupling of the SWOT and the reinforcement learning. So based on these studies, next I would like to extend this reinforcement learning to multi-reservoir control, because so far I was showing only one reservoir. And another subject that I would like to work in the future is to develop the interpretable machine learning models. So far that what I have developed is like making the model is just predicting some values and we don't know why. So I think I would like to I want to find out why the machine learning predicts certain values. So there are two major areas I think where I would like to work. One is the incorporation of the domain knowledge into machine learning, or either using the model agnostic methods to explain the behavior of the machine learning model.